I'd like to discuss the concept of work in physics. The work equation is given by a force times a displacement. Pretty easy equation. Work is force times displacement. If we want to look at the units for this, force, of course, is in newtons and displacement is in meters. And if we do this all in MKS, you'll remember Newton was kilogram meter per second squared. And if I take that then times meters, I'd have kilogram meters squared per second squared. That would be the MKS units for work. The nice easy units for this is called a joule. Joules of work. That's the unit also for energy, which means work and energy is actually the same thing. We'll talk more about that later. When we give energy to something, we're actually doing work on it. A couple things to notice about this is that force is a vector quantity, and so is displacement. And for work to occur, the force and the displacement vectors need to be in the same direction. They need to be in the same direction. So if I were to just walk across the room holding a marker in my hand, how much work would I do on the marker? Well, I wouldn't actually do any work. The marker would be moving across the room this way, displacement, but the force, if I'm holding the marker, the force is actually working upwards on the marker because I'm suspending it in the air, so I'd be holding it up with the exact force that would be equal to the marker's weight. So these two vectors would not be in the same direction, and therefore I wouldn't actually be doing work. I have to have the force vector and the displacement vector pointing in the same direction. That's key. The other thing is, what if I come over here to a wall and I push on this wall as hard as I can for a long time? How much work did I do? Well, I might get tired because I'm exerting a lot of force, but I'm not moving the wall any displacement. So by the physics definition of work, I'm actually doing zero work. I need to actually displace the object. So with those concepts in mind, and with a very, very simple work equation, we're going to attempt several problems in this lecture. So let's start. How much work does it take to lift a 1 kilogram mass 5 meters? How much work does it take to lift a 1 kilogram mass 5 meters? Well, of course, the equation for work is force times displacement. So how much force would it take to lift a 1 kilogram mass? Well, it's going to take the weight of the object. However much weight the object is, that's how much force it's going to take to lift it. So instead of force, I could put mass times gravity. That would be the weight. And then times the distance, which would be how far I'm going to lift it. So my mass is 1 kilogram. My gravity is 9.81. And my displacement is 5.0 meters. So if I do this all in 2 sig figs, I would get 49 joules of work. So, probably a little easy problem there to begin with. A little more complicated problem. How much work does it take to slide a 1 kilogram mass at a constant rate along a horizontal surface for 5 meters if the coefficient of friction is 0.3? So I'm trying to figure out work, and work equals force times displacement. And so work equals, all I really need to know here is the force, because I know the displacement right away is 5 meters. So all I have to figure out here is the force. So I have a box on a surface here, and I'm going to slide it along with a certain force, and this is the force that I need to put into the equation right there. I got to figure out what that is. Well, I'm going at a constant rate, which means this way I should have a friction force. Of course, I have the weight working downwards. I have a friction force the other way. So this force in the work equation is not a net force. It's the force that's working in the direction of the displacement. So it's this F right here. So this F is going to equal friction force, which means the F is going to equal mu times normal force. And of course the normal force equals the weight in this problem. So force equals mu times m times g. So if I put mu mg in for my force, my work will equal mu mg times d. And that's all the things I had. My mu is 0.3, my mass is 1, gravity is 9.81, and the d is 5 meters. So if I multiply all three of those together, I will get 15 joules of energy. 15 joules of work is what it would take there. Okay, let's do a much more complicated problem. Let's take an inclined plane. So here's an inclined plane. I'll make a big inclined plane. And I have a crate here that I'm going to slide up this inclined plane. Here's the crate. The crate weighs 850 newtons, so I'm going to draw that down there, 850 newtons. I can resolve that into a normal force and a parallel force. And this is 15 degrees here, 15 degrees. And the distance that I'm going to push this up the inclined plane, the surface here, right here, is 10.0 meters. 10.0 meters. I want to know how much work it takes to push this crate up the inclined plane. So we know that work equals force times distance, and my distance is going to be 10. So all I have to do is figure out what force am I, let's say, pulling the box up the inclined plane. Well, this is constant velocity also, and you'll see that I have a force downwards, a parallel force, always working downwards. I'm also going to have friction working down this way. So the force here that I need to put into my equation should equal this force plus this force. So what is friction? Well, friction is mu normal force. What is normal force? Normal force is, in this case, is going to be the weight times the cosine of the angle, which was 15, plus I have my parallel force, which would be W sine of 15. And so I could plug in my mu in this problem, and the mu was given as 0.24. My mu was 0.24. So I could plug that in. My weight is 850, and my angle is 15. And if I put all of that in there, I'm going to get a force right here and you should pause this and work this out on your calculator. I should get 417 newtons. So I'm going to take that and put that into my work equation. 417 times force would give me a work of 4,170 joules of energy. That's how much work I'm going to have to put into this box to get it to go up the inclined plane. All right. So that's a little trickier problem. What I want to look at, though, is it took that much work to move this box up to this location. Let's say this is the first floor here, or the second floor, like on an apartment. Okay, up to that point. You know, how much work would it take to have just, come over here and lift the box, to take this box, let's say this box is down here, how much work would it have taken just to take this box and, lift it straight up to here? Would it have been easier just to do that? So, how would I do that? Well, work is force times distance. Well, how much force would it take to lift this box? Well, that one's easy. Work would equal, the force it would take to lift this box would be whatever the weight of the box is, and it was 850. So that would be the force. That'd be very easy. Now what's the distance? Well, how high am I lifting this box right here? Well, we could actually figure that out because we know that this angle is 15 degrees and this inclined plane here is 10 meters. So this side over here would actually be 10 times the sine of 15. That would be this height right here. And if I figure that out, or I take 10 times the sine of 15 and I use that as my distance right here, I could find out a different work. This would be called the work output. This is what the work that's actually going to get done. 850 is my force that would take to lift that. And I would take it times 10 times the sine of 15. That would be my height right here. And when I do that, I get a work of 2,200 joules. Now look at that. This is interesting. To do the work that it took to push it up the inclined plane was 4,170 joules. But the work it would take just to come over here and lift it straight up to the top right here is only 2,200 joules. So that makes us ask a question. Why would I have wasted my time pushing this box up the inclined plane? Clearly, I'm doing more work pushing up the inclined plane than it would just be coming over here and lifting this box straight up. The reason is because to come over here and lift this box straight up, I would have to exert 850 newtons of force. Now, I wouldn't have to lift it very far. I'd have a short distance right here. But I'd have to exert 850 newtons of force. Whereas over here, I only exerted 417 newtons. Now, the reason I would use this inclined plane is because I might not physically be capable of actually exerting 850 newtons of force. So I wouldn't actually be able to do this work, even though it's less work than to push it up the inclined plane. It's all about the force. What force can you do? So I'm going to use an inclined plane and use a smaller force but move it a longer distance, rather than using a really big force and moving it a small distance. So inclined planes don't actually, or in any kind of simple machines, don't actually have you do less work. They actually have you do more work. But they make you do that work easier because you don't have to use as much force because you're going to use it over a much longer distance. We'll talk about a little bit about simple machines a little bit later. I'd like to look at one more thing. Let's look at this in rotational world. Let's say I want to rotate something. Well, to rotate anything or to move anything, it's still going to take work. Now, in our regular equation, work is force times displacement. So what is this? How does this translate into rotational world? Well, when we're applying a force in rotational world, we're going to apply it tangentially along to a radius of something that we're turning. So force in rotational world becomes torque. Some of you might remember this. The displacement will now be angular displacement. We called that Easter egg earlier. And of course then work would be Fr, the tangential force times the radius of what we're turning, times the Easter egg. So this would be an equation for work in rotational world. So let's say we have a wheel. We have some wheel here that we're going to turn, and it has a radius of 2 meters. I'm going to apply a 12 Newton tangential force here, 12 newtons of force to start this thing rotating. And I want to turn this thing around one time. I want to turn it around one time. So one revolution is what I want to turn it. I want to know how much work it takes to do that. So this is actually pretty easy. Work equals force. My force was 12. Times the radius. The radius was 2. And how far did I turn it? What's my angular displacement? Well, it's one revolution. It's one turn around. But how many radians is that? I need to have that in radians. Well, one complete turn, we know, equals 2 pi radians. So I'm going to take that times 2 pi radians there. And if I did that in my calculator, I'd have 24 times 2 would be 48 pi. 48 times pi equals, and my work would be 151 joules of energy, or 151 joules of work to actually rotate this thing. So this is the equation that we're going to use for a rotational world. If I want to do work to rotate something, that's the equation I'd use for that. This was a very long video, almost 15.5 minutes, but I hope we have a good grasp of the work formulas.